Great, thanks so much, Derek. And thanks to everybody who's attending. And I also want to say a big thank you to Ryan Winter for organizing this event and getting all the attendees invited. So basically, what we wanted to talk to you about today were case studies in hydraulic circuit performance. And what we wanted to look at specifically were die casting machines and some different options for control upgrades. Back in May, there was a NADCA plant management conference, and one of the highest priority topics that they wanted to cover during this conference was ways to improve productivity for die casters. And they approached us and wanted us to present on control upgrades as it relates to improving productivity, and we were happy to, because that's what we do here. And it turned out to be a very good presentation. We had a joint presentation with John Cleary of Avidal Cast, the caster up in Wisconsin, and there's a lot of good discussion during the presentation and afterwards. And we wanted to share the presentation with the people that were not able to attend the plant management conference. So a couple of weeks ago, we did to our general customer base, and then today, obviously, more specific to NADCA. The Chapter 7 folks. So real quick agenda, basically want to look at a couple different configurations of hydraulic circuits that we see that are common on die casting machines, and then talking specifically about control upgrades. There's a couple different paths, a couple different options. I want to cover a little bit about what those different paths and what those different options are. And finally, I have some case studies that are control system upgrades that our customers have implemented. And there's 3 case studies, and each one follows a different path to upgrade. I'll try and keep the presentation part to about 40 to 45 minutes, and then leave some time open at the end for any questions that come up. So we'll get started here. The first slide I wanted to show was a slide that I'm borrowing from the NADCA State of the Die Casting Industry 2017. This is from the executive conference that occurs every year. I thought this was important to show. Basically what the graph shows, all the blue bars are sales volume per die cast machine. And as you see, as you would hope to see, is general increase in sales. So starting in 1989 to where we are in 2016, you see a general trend upward. And over most of that time range, you also see the red chart, which is productivity, and you also see the productivity rise along with sales volume, which is good, which is what you hope to see until about 2014, when it levels off and actually kind of dips down a little bit. So important to show when we think about casting. A lot of one of the reasons that casting is used in so many applications. It's an efficient process, and it's also a good cost-effective manufacturing practice. But there are alternatives to casting. The steel industry is very strong. Some that consider stamping or forging, and in recent years we've seen parts that were made of steel come over to aluminum, which has been great for us. But if productivity is not maintained at a high level, and you lose some of those cost advantages. So as an industry, we feel it's very important to look at ways for casters to improve their productivity. And when we say productivity, some people say OEE. It's really the same thing. It's the measure of how efficient you are as a manufacturing operation. There's basically 3 components that go into this. Derek, who you just did the quick introduction, came up with this graphic, which I thought was a great visual, just to explain what you're missing when you don't have the optimal OEE. So of course, you look at your machine, you have unscheduled time that doesn't count against you. The machine's not supposed to be running. That's not necessarily a bad thing. But if you are supposed to be running, the first metric we look at is availability. So that's your A. anytime anything that knocks your machine out of production, that's gonna affect your OEE score and drag it down. The second metric that is included in OEE is your P, which is your performance, which is your cycle time, and that just relates how long it takes you to make a part for each cycle of the machine. Final metric is quality. Anything that counts against that is parts that are scrapped, that are made within specification and need to be scrapped. So I thought it was really interesting at the recent plant management conference. The top topic that people wanted to cover was improving productivity, and we do kind of like a roundtable discussion, and people throw out ideas about what can we do to improve productivity. And I was in the audience, and I was kind of listening to all of the suggestions that were being mentioned, but they all related to decreasing your cycle time. And that's good, and that's a really important thing to consider, but not too much of the discussion was aimed at reducing downtime and reducing scrap. The important point I wanted to mention about that is since we're talking about control upgrades, doing a control upgrade on the die-cast machine is a very good way to improve both the availability and the quality metrics of your OEE. So doing control upgrades can really improve your efficiency as a manufacturing operation. Then we talk about casting. We think about it as a holistic process. So it starts with simulation, and then it goes to die concept and continues on through processing and process monitoring. And you look at this and you say, we need all this in the die casting process. And you take anything away, it's going to adversely affect. But then you also want to say, prioritize within this process. What are the most important things, and what can I get the most bang for the buck, and what do we want to prioritize on? I think if you ask most experienced casters, they would pick out two properties on this process, and first and foremost is die concept. You can't have a good process, and you can't make a good part without a good die concept. So that's really important. But of equal importance is also shot control. So making sure you have a machine that is capable of doing optimal shot control. So in the presentation today, we're going to focus specifically on shot control. And when we talk about anything, the topic here is shot control. I always like to start by saying what are our objectives. So if we wanted to implement shot control improvement optimization, what are the things we want to consider as objectives? And first and foremost is we want to have a machine that is both accurate and precise, which is displayed in the graphic here with the dartboard. So accurate is you're on target, and then precise is consistency, is repeatable. In the plant management conference, another one of the presenters was Hal Gerber of Shiloh Industries, and he had a good tangent in his discussion about how the method of casters. We have simulation, we have die concepts, we have experience. We put those are all ingredients that make up our process. And now that you have that process defined, you want to be able to make it repeatable. Make sure your machine is capable of accomplishing what your method is telling you to do. So shot control upgrade will give you this ability to be accurate and precise. And like we mentioned in the previous slides, OEE productivity. If you're looking for ways to eliminate downtime, increase availability, to improve your A metric of your OEE, as well as cut down on your scrap rate, which is the Q metric. Again, shot control upgrades are a really good way to accomplish that. We talk about flash too. I mean, flash has been synonymous die casting, as long as die casting has been a practice. And it's still there. I still go in a factory. I still see people flashing with die. We still see this as a problem. You think, sometimes people get involved with casting and they think, well, flashing, well, it's always been a problem. It's just something that I have to live with. Well, the reality is, with advances in technology, flashing your die doesn't have to be something you have to do on a consistent basis. There are methods to implement on a machine that can eliminate flashing. And again, shot control upgrades are one of those options. Scheduling flexibility. So we look at what volumes have been coming into the casting industry right now. It's been busy the past couple of years. So you always want to have your machines in operation, running optimally, so you can handle any scheduling or changes in customer demands. And then I think to kind of illustrate this point, let's look at a real basic operation. Let's just say you have two machines in your casting operation. One is a high performance machine that will handle the more demanding parts, and the other would be a low performing machine that can handle the parts that are not as demanding. And on typical scheduling, you're fine. But what happens if you see an uptick in the high performance parts? You can't ship that production to a low performance machine. You won't be able to make the parts to the specification that your customer is requiring. If you had an uptick in the lower demanding parts, then you can certainly run those on a high performing machine, but you cannot run a very demanding part on a low performance machine. So why not consider upgrading the machines that are not capable of giving you the performance that you need into a high performance machine? So again, shot control. Finally, in terms of objectives, we want to look at operating costs, and we want to keep those low. So are you having a lot of spare parts on hand that you need to keep just to keep your machine running? Are your maintenance personnel spending a lot of time on the machine? You have a lot of downtime machine. These are all costs that affect your operating costs. We want to make sure that as a caster, you're really looking at all those costs and looking at ways to eliminate unnecessary costs. So really, really important, because shot control can help you out on those aspects. And then after looking at objectives, we look at considerations. So you've got a die casting machine. What do I want to consider in terms of could it be upgraded and should it be upgraded? And sometimes we come into machines and we look at them and say, it's not even worth the machine is in such poor condition that it's not even worth investing more money to get this machine improved. And then we talk about machines, like snapping tie bars with another stay square. So machines like that, you're probably better off just scrapping the machine and getting another one to replace it. But let's say the machine is in good enough condition, it has been maintained, there's just certain things that are lacking. In those instances, you want to evaluate the machine and consider which one of the upgrade paths would make sense and would be best for your machine. One of the big determiners that's going to do that is to look at the hydraulic layout. You've got your hydraulic schematic and everything's piped together on your machine. So you want to look at that. And some of the things we look for is, does the machine have a close coupled accumulator? Is the hydraulic circuit neat? Is it efficient? And is it too complex, or is it simple? And I kind of illustrate this point too by pointing out my experience in the die casting industry is 4 years. So I started with Visi-Trak in 2013, and before that I worked for Barker Hansen distributor, and we sold hydraulic technology, but to general industrial applications. So we could have been on a steel mill, we could have been in a food processing plant, we could have been on transfer equipment. For us, 100 gallon per minute valve was that was a huge valve. It's really large, and I still remember my first application that I sized when I was at Visi-Trak was for a 900-ton machine. And I said, well, 900 ton, is that a large machine, or where does that go in the range? It's not 900 ton is kind of in the medium to the low, because we've got machines that go up to 3,000, 4,000, 4,500 ton. And I know I've heard of now in Germany there's a 6,000 ton die cast machine. So anyway, this was a 900 ton machine, and I went out and sized it, and I came back with 1,350 gallons per minute. Comparing that to the 100 gallons per minute, that was my experience prior to. I said, what did I do wrong? But the truth is, I didn't do anything wrong. I had the calculation was correct. It's just that in die casting, you're moving. It requires high force because you're moving a large mass of molten material into a die, and you also need to move at very rapid speed. So the hydraulic layout on a die casting machine is very unique as compared to other technologies. So really important to hear your hydraulic layout and make sure you, yeah.
Sorry to interject. We were noticing that you're getting a little, picking up some stuff on your mic that's a little bit of background noise, and I don't know if maybe it was not plugged in correctly, so if you could just check that.
Okay, I tell you what, let me fix that. Does that sound a little bit better now?
That's a lot better. Sorry to interrupt.
I apologize.
Thanks.
No problem. Sorry about that. Okay, so and then after hydraulic layout, we want to look at cost. Cost is always going to be a consideration. So what there are different paths to consider, and those have different costs associated, and I'll cover some of that in some of the later slides. Okay, and then you also want to look at the layout of your facility. So let's just say your facility was full of 900-ton machines, but now your customers are asking for parts that might require a larger tonnage. So, are you going to be able to fit a larger tonnage machine in your facility as is? Do you need to bring in new cranes? Are you going to be able to get metal to the new portion of the new machine? And just other things to take into account is basically like the layout of the facility. And then, finally we say, what is the customer demanding? What is the market demanding? So we're seeing a large increase in structural, weldable, high integrity castings. So is your machine capable of accomplishing, making the parts that the customers are asking for now? Castings are only going to get more challenging. Nobody's asking for the easy castings out of the North American market. And then finally, your customer also wants to know your scrap rate. So they do not want to accept any scrap. They don't want to get any bad parts that you produce, and they also want to know that you as an organization has a low scrap rate, because it means less probability that they will actually get a bad part from you. So a lot of customers are asking to know what your scrap rate is on your machine. So again, doing shot control upgrade is a way to accomplish a lot of these considerations. This is a quick little slide. Slide just to illustrate a point, and I'll admit it's a little bit hokey here, but let's just go with it. Let's say you were considering a Corvette, and two of your big considerations are going to be cost and performance. And as you can see, if you went with a brand new Corvette, there's a cost associated with that, somewhere in the $79,000 range. But you could also consider a pre-owned Corvette, maybe in the 20 to 25-year-old range, and you could get that for a much lower cost. Cost difference in this $60,000, $65,000, $68,000, something like that. And you say, is the better performance, but you're going to get the better performance with the newer vehicle. So you get the larger engine, you get more horsepower, you get your 0 to 60 is a lot faster. So how does that balance out? Well, what if we considered that there was a box of parts that you could buy that you could implement into the older Corvette, and you could get performance that either approaches or matches the performance of the brand new vehicle. And is this realistic on a Corvette? Well, probably not. And how much? But in a die casting machine, we have taken machines that were 20, 25 years old and had them perform just as good as a brand new machine. How much is that box of parts going to cost? That goes back to our slide about considerations but what the other side of it is the performance side. And when we're talking about your machine and your performance, you want to have a very responsive system. A lot of casters are taking a approach. It's called MFT, minimum fill time. So you have a very slow, drawn out advance of the metal to the gate, and then once you get metal at the gate, you want to ramp up to a very high speed and a very rapid acceleration. And this is just a couple examples of what we've accomplished using our control system. The first I'll cover is the graph to the left. I'm assuming most people on the conference call understand how the shock trace works. So we're looking at velocity in the vertical and our position in the horizontal. The one to the left is a 2,500-ton E-drill machine that was equipped with a 100 millimeter Olmsted SV series cartridge valve and a Visi-Trak control system. And they were able to accomplish in only 16 milliseconds, they were able to go from 10.9 inches per second to about 327 inches per second. So we talk about explosive acceleration and that rise time of how long it takes to get to your fast shot speed. Being able to minimize that, that's a big benefit in the casting process. The other two examples here, these are just some other machines, but if you're into the metric system, we've got in the top on the right, so they're going from 0.467 meters per second all the way up to 10.8 meters per second. That's only taking 17 milliseconds. And then to get back to the English units, we're going in this bottom right. In this instance, we're going from 30 inches per second to 233 inches per second in only 11 milliseconds. So now I'm going to kind of focus on some different hydraulic circuits that we encounter on die cast machines. And the first I'm going to look at is meter in with brake, and in total we'll look at 3 different configurations, and each one is could be identified with the being made in a certain geography and of a certain vintage. And this one is typically seen in the Chinese market, where it's a meter in and a brake valve. And the basic principle here is you've got your injection cylinder, and I'm going to get my laser pointer going. So you've got your injection cylinder, and when you're injecting metal, your cylinder is extending basically over to the right here. And we've got an accumulator that's fully charged up. We will have a high-performance proportional or servo-operated cartridge valve, which is in charge of modulating the flow from the accumulator into the head end of the injection cylinder. And basically we'll open this valve a little bit to get a slower speed, and open it a lot to get a faster speed. And we'll use this high-performance valve for both the slow phase and the fast phase of injection. And when we need to stop the forward movement of the cylinder, so you can't stop it completely from here by closing this valve. You've still got the forward momentum. You've got all this fluid on the rod side. So what we'll do is close this valve off on the rod side, and that'll stop that'll basically stop fluid from moving out, and that will stop the forward movement of the cylinder. So that's a meter in with brake hydraulic configuration. The second configuration we'll look at is what we call a meter out circuit, and the meter out circuit is pretty typical of a machine built in North America. Prince and HPM basically manufactured to this this concept. And same thing. We've got an injection cylinder being fed by an accumulator. In this instance, in order to start movement, we will open up this blocking valve, and that gives full pressure, full flow capability into the head end. And in order to control speed, we will have a high performance valve on the rod side and modulate this valve to again a slower speed will open this a little bit to have a little bit of flow, and a faster speed will open it a lot to get a faster flow. I'm sorry, yeah, a little faster flow and faster speed. In this circuit, we're controlling all three phases of the cylinder's forward movement with the high performance valve. So we're doing slow phase, fast phase, and low impact, all with one single high performance valve. The third and final configuration we're going to look at is what we refer to as a double meter in and a meter out. So you've got three different phases of movement, and you've got a separate high performance valve to handle each separate phase. And you'll size the valve in accordance with whichever speed that you need during that phase. So you'll have a smaller valve to do your slow and intermediate valve velocities, and then you'll have a larger valve, and this will probably be the largest valve in your circuit, which is in charge of modulating flow into the cylinder during your fast velocities. When you need to stop after your die cavity is full, now you want to stop forward momentum of the cylinder, you'll be able to ramp it down with this what's referred to as a low impact valve. And this, again, this will be sized in accordance with what the flow rate out of the rod side of the cylinder is during being able to ramp down from your fast phase down to low impact. Looking at all three circuits, just do like a little compare and contrast. Again, talk about cost and performance. Out of the three different options, they'll have different costs. Think about which one would be the most expensive. Well, the double meter in with meter out has three high performance valves, so that in terms of upfront cost and spare part cost, this configuration is going to be the most costly, the highest cost associated with it. And then let's talk about performance. So we say, what's the performance of each different configuration? Well, we do have a high performance valve on the meter in for your slow phase and your fast phase velocities, so you can get good performance out of that. But when you talk about your end of shot position, in these instances, this brake valve is usually just a solenoid operated valve, which is being commanded by a PLC, which has a scan rate. And the faster you go, that scan rate may not be able to keep up with and be consistent. So you also have a response time associated with this solenoid valve. So in other words, we give a signal to say close. It's going to take 30 milliseconds or whatever it takes to fully close. We tend to see the not very good performance on end of shot, meaning flashing for this configuration. So this is a configuration meter inlet brake valve that we really don't like to recommend. Now we'll focus on the two configurations to the right. We've got three different high performance valves, and they're sized according to the application, and that's good. So you can have a valve that's sized according to what you need during your process. What I want you to consider is that you're also trading control from valve to valve for the different aspects of your motion. So are the valves trading control at the exact same time? We've seen some good performing machines where they do, but we've also seen that in this configuration that some of the calculated start fast shot and then shot positions aren't the best, aren't optimized in terms of repeatability. And part of what I want to mention too, and when we see this circuit implemented, while they are high performance valves, they're basically general industrial valves. So they're made to handle a wide range of applications, and not necessarily optimized specifically for die casting. But when we look at the meter out circuit, we also do see general industrial hydraulic valve be implemented in these circuit, and they work okay. Why we see better repeatability in this instance is because we've only got one valve doing it, so we don't have to trade off control. So we tend to see better performance using the meter out circuit. But when we see the best performance out of the circuit, and when we also implement the valve that is designed specifically for the die casting operation, which is the Olmsted SV valve. So this is a valve that's a result of a joint development between Olmsted Products and Visi-Trak, probably back in the late 90s or early 2000s, and it's a tin cartridge, meaning wherever you are in the world, people can manufacture the specs. So your Parker Hannifins, your Vickers, your Bosch Rexroths, everybody makes the valve to the specification, and what that allows you to say is wherever I am in the world, I can have confidence that I'll be able to acquire a valve that'll fit into this hydraulic circuit. But the real benefit of this valve is that, again, it was designed specifically for the die casting process. So it is designed to handle your slow phase, your fast phase, and your low impact phases. And one of the reasons, the big reasons that we're able to do that is because of the flow window. And when I say flow window, this is the path that the hydraulic fluid follows to get out of the cylinder and basically back to tank. We're modulating it in this flow window, and you can't see it great in this picture, so I'll just kind of like draw it out. They call this at the factory, they call it the bike seat, just because it's kind of in the shape of a bike seat. And it's basically what the principle here is for slow phases will be in this metering notch here, and just allow a little bit of flow. That's when we can do a real fine, precise control on the slower speeds. When you need to ramp up into a fast speed, now we have this complete flow window available, which will allow a lot more hydraulic fluid over the valve, so you can get the really fast acceleration. Yeah, I mentioned in the previous slide a lot of the other valves that are used in die casting are just general industrial valves that are designed to handle many applications. And what you'll see is just like a circular pattern, and maybe they'll put a couple circles here, and that's good because it's easy to manufacture. You can just drill a hole, and the hole's easy enough to drill. a lot easier to make than making this bike seat profile here. But what you don't get is you don't get the nice nice properties that you get with this custom flow window of being able to handle very slow rates and accelerate into a very large flow window, and back down when you need to go into low impact. Part of what allows us to accomplish this also is the internal poppet here. We've got a very lightweight gate that allows very fast and nimble response. So we have a servo valve that we pilot this gate with, and we can get really fast responses out of it. And so if you wanted to go from a very slow speed into a very fast speed, you want to be able to have that gate to be able to move very rapidly within this flow window. And we're able to accomplish that because of the way that the valve is built. The final point that I wanted to mention on this on the Olmsted valve is that it's also an LVDT feedback. That's what really allows us to do our true closed loop control. Obviously, when you're doing a control, you want to look at the speed of the cylinder, but having this LVDT equipped on the valve, that also allows us to look at the position of the valve, and so we can tune and we can kind of anticipate what's going on in your system. If anything changes throughout your process, the valve will be able to change accordingly. So, real basic that I like to tell when we talk about closed loop control is, consider if you were starting up a cold machine. Hydraulic fluid isn't warmed up yet, so it's not very viscous. And if you open that valve up 50%, you can only get so much fluid through that 50% opening. As the day goes on, the oil heats up. Your machine gets into process. Now the oil heats up. Now it's more viscous. So that same 50% opening, you can flow a lot more hydraulic fluid through. If you do closed loop controls, we'll do that specifically on your speed. So it allows us to be a lot more repeatable, no matter what what speed you're commanding. Also, the LVDT allows you to do some diagnostics. So when you're setting up, when you're tuning the valve, you can look at this, look at the LVDT feedback and know where you're at. And if you're having any troubleshooting, you can command the valve to do different things and make sure that what you're commanding is also what you're actually seeing on the valve. So now I'm going to talk. I'm going to forward into the portion where we'll talk about what are our options in terms of upgrading a machine. And obviously, this is a die casting machine here. One upgrade path, and I referred to this in one of the initial slides, is what if your machine is so far gone that it's not even worth upgrading? Well, you could buy a whole new die casting machine. And that's what we're showing here. But let's consider the next level down. Let's say the machine was maintained well throughout its life, and the injection end is not in very good condition, but the tie bars are still good. Everything is maintained good on the clamp end. The linkages are good, and the platinums are you're able to square those up. Well, in those instances, we would say, why not keep the clamp end, but replace the shot end? And basically, I'm just going to draw what that would look like. So in that instance, we would keep everything on this end, but then build a completely new shot end. And there's companies out there that offer brand new shot ends. I would say two of the most prominent in our industry are Diecast Press and ITL, who are regular customers of Visi-Trak, and they're happy to implement Visi-Trak's technology into new shot end. So that's one upgrade path, is to replace the shot end. Next in the in a little bit less than a new shot end would be to consider is what we refer to as a modified hydraulic circuit. You know, in this instance, the clamp is still good. Most of the injection cylinder and everything on the shot end is in pretty good condition. So the shock cylinder is good. The accumulator is close coupled, but the hydraulics that control your injection movement are kind of lacking. So in those instances, we would eliminate the existing hydraulic circuit and implement a new hydraulic circuit using the Olmsted valve. Of less complexity is what we refer to as just implementing our valve. And on these machines, they already have a DIN cartridge valve cavity. All we need to do is take out a valve, install a new valve somewhere in this region, and then we can implement the new valve plus the Visi-Trak control system and accomplish a control upgrade. And then the final upgrade path is let's say you just want to keep your hydraulic circuit as is, but then just implement a new hydraulic control system, and we can accomplish that also depending on the configuration of your machine. So again, those are your upgrade options, starting from the most costly and then ranging down in terms of complexity and cost. And now I'm going to shift into the couple case studies that we have to show, and we're going to go the other way. Now we're going to start at one of the easier, not very complex control upgrades to implement, and then the following two are going to be a little bit more costly and more work to implement. But this is a nice case study here. This was the portion that John Cleary of Allcast presented, which was taking their they had a relatively new LK machine that was in their facility, and they were doing okay with it, but they had a couple reasons why they wanted to change it out. So they went ahead and implemented the Visi-Trak control solution, and this was fairly easy to do because all we needed to do was implement our control system. They already had a hydraulic cartridge valve in the circuit, so we simply needed to remove that valve and then in its place install the Olmsted valve. We also implemented our sensing technology. This is really one of the best ways to know your position, velocity of your injection cylinder. Visi-Trak was one of the pioneers in this technology, which has since been copied by many die casting applications. So what I've basically done is taken what John's presentation is and kind of condensed that. But this was a nice quote that he shared, and kind of speaks to how the casting industry has evolved in the 30-odd years that he's been. So basically, when he started in 1982, if you controlled 95% of your variables within the casting process, you had a good chance of making it an acceptable casting and having a good process. But with advances in what casting customers are asking for these days, you now pretty much have to get 100% of your variables in control to make sure you have a quality casting and a good process. So he shared a little bit about what their path to control was, and it was actually pretty similar across much of our control base, customer base, where they started with process monitoring on a single machine, and once they had our monitoring system implemented on one machine, they quickly followed suit on installing monitoring on all of their machines because of the benefits that it brings with it. Then in 2004, they got started with their first control upgrade, which was an 800-ton Prince die-cast machine, and since then, they've now got a total of 7 die-cast machines, which have implemented Visi-Trak SureTrack control system. And why upgrade? They looked at it. They already had the monitoring on all of their machines, and they were seeing these variants in what was the performance on their machines that were controlled by the SureTrack control system, and what was the variance on the machines that were controlled with PLC machine control. And what I'll show in the next couple slides is, they were able to get consistent performance out of their SureTrack controller, but not so much off of their PLC machine control. And it goes back to why is that? Because a lot of their PLC machine control, you're dealing with a scan rate, which may not be optimized to the casting process. And you're also dealing with solenoid operated pilot valves, which have a response time associated with them. So the repeatability when you're going high speeds is not that great. Here's what they found. I mean, this is a comparison. On the left would be their machine, which is controlled with just a PLC controller, and on the right is the Visi-Trak controller. And calculated startup fast shot, very important process parameter to casting. If you start too early, you will not be, you want to be accelerating metal into the die cavity. But if you start your fast shot early, you won't be. You're going to get caught. You're going to get caught at that gate, and you won't get good performance. And same thing, if you start late, that's problematic as well. But as you can see, the results with the PLC control, they did not get consistent. They were not getting consistent performance. But with the SureTrack controller, very, very good consistency across their process. For those that are really familiar with Visi-Trak, I'll mention this is we have a feature in it where we can overlay. So from cycle to cycle, we'll put shots on top of another, and it's just a good way to check repeatability. And this is just a picture from one of their processes, and you can see with the SureTrack controller, they're calling for it, they're hitting it, and they're just repeatable on top of it again and again. We also did a intensification control through our control system, so not only the injection, we can also control from a electrically driven proportional or servo valve. We can control their intensification process. And again, you can see that in the process parameter, it went from a very unstable, not repeatable process to much better consistency in the SureTrack controller. What was the process like for them? John shared that it was very efficient, and this is the process that they followed. They installed the Visi-Trak control system, removed the existing OEM supplied cartridge valve, installed the Olmsted SV valve, and interfaced the intensifier control valve to our control system. So they did the first one, and it only took about 2 days. And then after that, they did 2 more machines on site, and when they upgraded those machines, it was down to like a 4-hour upgrade. So they were taking these machines out but getting them right back into production, which is a very very good performance. And what were the benefits? This is direct from John Clary, and we love to see this feedback. There were basically uniform throughout their process. All their process control technicians only needed to learn one system. Their maintenance personnel only needed to learn one system, and all the spare parts were good across their entire floor. And again, this was written by John Clary, so excellent customer support. Thank you. It was very, very nice to hear, and also very important from us at Visi-Trak. So the next case study we're going to look at, number 2, this is the control upgrade that we implemented at Metaldyne in Twinsburg, and this is where we're going to do a modified hydraulic circuit. So in this instance, the clamp, everything was good on that side. Most of the shot end hydraulics were in good shape, It was just the hydraulic circuit was not optimized, and we didn't have a path where we could just simply insert the Olmsted valve. We needed to make some changes to the way the hydraulic circuit was piped, and this is a picture of what that looks like. In near the end of 2013, we started talking to Metaldyne, and they had a project that they wanted to. These were some of the objectives, what they were looking at. They had one machine in particularly where they wanted to improve part quality, and they felt they could do so by improving the accuracy and consistency of these 4 process parameters. And I think if any caster will agree that those are critical process parameters. So they wanted to look at ways they could get better performance there. They also had a high incidence of flashing on this machine. And they also had a lot of work scheduled on this machine, so anything that they were going to implement, they needed to do so in a way where it would get the machine back into service ASAP. They had a lot of downtime on this machine, so the maintenance technicians were spending a lot of time. They had to purchase a lot of spare parts to keep the machine running, so ways they could eliminate those hassles. And also looking ahead to what their customers were demanding. Just being able to improve the capability of the machine was going to be really important to them. And they considered a number of different paths: new machine, new shot end. Ultimately, what they decided was what we presented, which was for their machine, which was built in 1994, and this was upgraded in August of 2014, and consisted of the controller, the valve, a servo valve, and a conversion manifold. When we did this conversion manifold, we wanted to do so where it would not impact the machine too greatly, and we'd be able to reuse a lot of parts of the circuit. So what you'll notice on the tank line is that we were able to reuse the tank line. So we had to do some measurements to make sure everything was going to line up properly in terms of that. We'd be able to mount right back in. But we were able to accomplish that. And here's some other pictures. This is just from the other side. We also implemented intensification pressure control on this upgrade as well. But what did they accomplish? Well, this is a statistical analysis going over the 4 process parameters that they wanted to improve. In each one of these graphs, the blue line, this blue vertical line, demarks when we actually did the upgrade. And you can see they went from an unstable process, which was the before. After the upgrade, we got process consistency across all these parameters. So when you're considering a control upgrade, I mean, this is exactly what you want to accomplish. So some of what they were also able to accomplish, things that they, some tools that they didn't have, is we gave them the capability to ramp, which they didn't have before. Now, if you just jump from a slow speed to your intermediate speed, you could create a wave front here, which will result in porosity. But if you do, you can draw this acceleration out, pretty much the whole way you could if you want. They only do this portion here. But you want this basically uniform metal flow where you're not going to trap any gas within the metal. What you also notice is what we refer to as the rise time. You'll kind of see a relatively gradual increase in speed until they attain their fast shot speed. But with the Visi-Trak control system, it's very, very rapid response in terms of getting to the fast shot speed that they were commanding. So what were the results? First of all, we were able to accomplish getting their machine back in a very fast time frame. So in the first machine that we upgraded, it took 5 days to implement the hydraulics. In subsequent upgrades, we got that down to about 3 days. As I went through in the previous slide, they did accomplish the marked improvement in accuracy and consistency for those critical process parameters. And flashing was almost completely eliminated on this machine. So once we did the first machine, they took the parts of the X-ray, got approval, they went into production, and they were real happy with it. What commenced afterwards were a couple studies that they wanted to look at internally. So one of the studies that they did was a machine utilization, where they took 3 machines running the exact same part at the exact same time, and one of the machines had the Visi-Trak system, and the other 2 just ran on the original OEM supplied system. And compared what did they see on the different machines over a couple production runs. They found that it was a 20% increase in machine utilization on the Visi-Trak system, which is big impact, very good improvement, and that's what led them to upgrade 5 more machines the following year. What also helped that decision along was their ROI study, which was a longer term evaluation, and they just looked at machine uptime, how much time their maintenance personnel were spending on the machine, the components that they were needed to replace, and any leaking components that they needed to replace, and decrease scrap. And they calculated a $16,000 savings per month on the single machine, which equated to about an 8-month ROI. And the thing I really love about the ROI is it paid for itself in 8 months, but they're still taking advantage of all of that process optimization. As well, the machine is now capable of handling the advanced castings because of improved injection performance. We'll send out this presentation afterwards, but if you want to read this in a little bit more, this case study in a little bit more detail, there's a link here that just takes you to our website. And we had a report that was published in Die Casting Engineer magazine back in, I think it was July 2016. In the final case study, and I'll kind of wrap this up here, is a new shot end. This is a new shot end that was built by Die Cast Press, and this was on an Ube machine. There was no path on the Ube machine. We could simply implement the valve, and we couldn't really change the hydraulic circuit. The only real path to upgrade was a complete new shot end. That was, the previous slide was at the factory as it was built, and then this is at the customer's site where it was implemented. But why did they choose a control upgrade on theirs? They weren't able to go. They weren't able to achieve the performance. They were calling out. They were programming their machine to do one thing, and they were not getting that, and they were not repeatable. So this is our overlay chart. Not even, there's no process consistency there. Once they implemented the new control system, you can see the reference traces in red here, and the actual trace is in green, and you can see where, as we say, rock solid in here to the master shop profile. And then overlay, how repeatable are we? You can see really good repeatability in this on this machine. With that, I'm going to kind of wrap it up. The final slide here is OEE. We talked about what the A, the P, the Q mean. World-class OEE is 85%. So, the last thing I'll mention here before we open up for any questions is, control upgrade is a really good way to look at the A and the Q metrics of your OEE. So, get you closer to this 85% rating, which is considered world-class. So, thanks everybody.
Thanks, Eric. Yeah, and we'll go ahead and answer a couple of questions here. We realize we're right at our time limit as well, so if anybody needs to hop off, we understand that. We'll certainly, if we don't answer your question here right now, we'll follow up with email, and as Eric mentioned, we'll also be sending out a link to this presentation to you as a follow-up email. So just a couple of things, Eric, that came up. One is, what is the operational life of the SV valve once installed and kind of ongoing?
Yeah, sure. So the valve is there's 2 components to it. One is the cartridge valve, which is what we consider the old Olmsted valve, but then there's also a servo valve that drives it. If you want to say the consumable of those is the servo. It's just because it's a little bit more touchy when it comes to contamination. And we've seen all ranges of life on the servos. But if you keep the fluid clean, and maintenance on the valve within good practices, certainly 5 years and above, we've seen as being pretty typical for the servo. The Olmsted, the cartridge itself, is even longer than that. I mean, we've seen 10 plus years of operational life on the Olmsted SV valve with good fluid practices on that.
Great. And then another one was in terms of hallmarks of a machine that has been maintained and is a good candidate for the hydraulic upgrade. What are some things to be looking for? You mentioned a few things to be looking for, but what are some things that maybe make you sort of question whether or not that machine's quite capable of an upgrade, or is there any real trouble spots?
Yeah, I mean, the first thing is we always ask for the hydraulic schematic, and we want to look and see what that design is. At least either if we can't visit on site right away to evaluate the machine, just looking at the construction, even in pictures, and how the machine was constructed, that'll tell us a lot about whether or not it's a machine that's a good candidate for an upgrade. So, I mean, those are two things we always ask for right off the bat: hydraulic schematic and some pictures of the machine. We'll be able to at least give you an indication whether or not it's a good candidate for upgrade from there.
Great. Well, with that, I think we'll go ahead and close things down. We're a couple minutes over, but as I said, we'll send this presentation out to everyone who registered, and if you have any follow-on questions, I'm sure Eric would be happy to answer them as well.
Absolutely. Thanks, everybody.
Thanks, everybody, for your attention, and thanks for joining us. If you have any follow-up questions, please let us know.